All right, this is the video for Calculus BC, section 9.7. This would be part B to go along with part A. If you haven't watched part A already, you probably want to do that. Make sure you know what we're doing here. So we're going to start off with number 4 in your notes in this section. And number 4 says find the third degree Taylor polynomial for f of x equals sine x expanded about c equals pi over 6. So if you remember that basic Taylor polynomial construction, we're going to start off by writing p of x. P stands for polynomial. You could write t of x if you wanted to for Taylor. But here we go. The first term is going to be the function evaluated at our centering point, and our centering point is pi over 6. So it's going to be f of pi over 6, which of course would be sine of pi over 6, which is 1/2. So my first term is going to be 1/2. Going for third degree. We're up to the 0th degree. So our next term is going to be based on f prime of x, and f prime would be cosine. So f prime of pi over 6 is equal to cosine of pi over 6, which is root 3 over 2. So my next term is going to be plus root 3 over 2 times x minus pi over 6. Okay, we're up to the first degree. Got 2 more degrees to go. Second derivative is equal to negative sine of x. So f double prime of pi over 6 is equal to negative 1/2. So this is going to be minus 1/2 times x minus pi over 6 squared all over 2 factorial. And then our final term here, we're going to third degree, so our final term we're going to need f triple prime. So f triple prime of x is equal to negative cosine of x, and so f triple prime of pi over 6 is equal to negative root 3 over 2. So my final term would be minus root 3 over 2 times x minus pi over 6 to the third over 3 factorial. There's a bit of cleanup work we could do here. None of it is really necessary unless we need to match it up with a multiple choice answer. Looks something like this, I guess. Root 3 over 2. Nothing's really changed here. But over here, we could end up with x minus pi over 6 squared over 4. And this could be minus x minus pi over 6 cubed over 12. That would be, if we simplified a little bit, but not something we have to do unless, again, we're matching up with a multiple choice answer. Okay, so we're going to do a couple more here. Take a look at number 5. Number 5 says, the first 3 terms of the Taylor series for g of x are the following terms. You see them right there, the first 3 terms. What is the value of g double prime of 0? Pretty common question. And so here's what we're going to do. We're going to look at the basic construct for Taylor series. So a Taylor series, a Taylor polynomial, is equal to g of 0 plus g prime of 0. And then you can see we're centered at 0, right? And they're all just x's and x squareds instead of x minus somethings. And then the third term would be g double prime of 0, x squared over 2 factorial. So what we would do here is we would use that to help us match what we have in our polynomial. So I would say, you know, this obviously is our first term, this is our second term, this is our third term. And what I would seek to do is I would try to match the 3 and the 5 with this over here. I think what we could do then is say that 3 over 5 equals g double prime of 0 over 2 factorial. See, they're in the same places, right? So based on that, I think we'd have a pretty easy time solving that. I think we could then say that if we multiply both sides by 2, we would get 6/5 equals g double prime of 0. So we never know what g of x is. We never really know exactly what g double prime is, but we do know that g double prime of 0 is equal to 6/5. Okay, I think we got a few more examples to go here. Let's see what we can find in these last, I think the last two. Yep. Okay, so a couple of important ones coming up with numbers 6 and 7. Okay, so number 6, find the first 4 non-zero terms and the general term for the Taylor polynomial. And I need to put this in here. I'll put at c equals 0. So if you have a Taylor at 0, that's just another way of saying what? A Maclaurin, right? So here we go. This is something we have talked about a little bit, and we're going to kind of get this maybe put together right here. So I'm going to say p of x for my polynomial is equal to, first term is going to be f of 0. So f of 0 is equal to e to the 0, which is just 1. What's nice about this is all my derivatives are just going to be e to the x, right? So, second derivative, et cetera, they're all going to be e to the x. So this is going to construct pretty easily. So we could put plus f prime of 0 would also be 1, and f double prime of 0 would also be 1. So they're all just going to be 1x plus 1x squared over 2 factorial plus 1x cubed over 3 factorial, so on and so forth. Hopefully you can see that the nth term would be plus dot 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 plus x to the n over n factorial. Of course, you don't need to write all those coefficients of 1s. You could just write 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. Okay, so we've talked about that a couple times. That's actually how you construct it. All right, and then finally we have number 7. And number 7 is pretty unique and pretty special. So this says find the first 4 non-zero terms and the general term for the Taylor polynomial. And again, I'm going to say at x equals 0, making this again a Maclaurin. But here we go. As is typical, I'm going to write p of x equals. And the first term, of course, is just f of 0. So f of 0, I'll just do this up here, f of 0 is equal to 1 over 1 minus 0. That's just 1. Okay, so we got to do some derivatives here. Of course, this is equal to, this will be helpful, 1 minus x to the negative 1. We do our derivatives, that's going to be pretty helpful. So f prime of x is then equal to negative parentheses 1 minus x to the negative 2. All right, so that means that f double prime of 0, or excuse me, f prime of 0 is equal to negative 1. Except we forgot the chain rule. Sorry about that. So times, should have a times negative 1 right here. So times negative 1, of course, we just get 1. So our second term is plus x, 1x. Okay, second derivative of x is equal to, it's going to be differentiating what we had up here. So that's going to be negative 2 times 1 minus x to the negative 3, again, times negative 1, making it really a positive 2. Okay, so if we evaluate f double prime of 0, we end up with 2. So that would be plus x squared, excuse me, plus 2x squared over 2 factorial. Already kind of an interesting pattern. Let's see if that continues. Our third term and our last term is going to be f triple prime, or it's going to be derived from f triple prime of x is equal to, let's see here, it would be negative 6 x minus 1 to the negative 4th, again times the chain rule, or oops, 1 minus x. Goodness gracious. Negative 6 times 1 minus x to the negative 4th times negative 1. Okay, so we evaluate this at 0. F triple prime of 0 is equal to positive 6. So we get plus 6x squared over 3 factorial. The pattern might not be super obvious at the moment, so let's do a little simplifying, and I think you will see a little bit of a pattern here. So here we go. P of x is equal to 1 plus x plus, please note that the 2's are going to cancel out. Right? 2 factorial is just a 2, so we get x squared. And then also notice that 3 factorial is just 3 times 2 times 1, also known as 6. So this 6 would cancel with this 6. Goodness, that should be an x cubed plus x cubed. Yeah, so I think if we found, if we kept on going here, maybe I will. Let me go with fourth derivative. I think we'd see this pattern continue. So fourth derivative of x would be equal to 24, negative 24 times 1 minus x to the negative 5th times negative 1, once again making it a positive 24. So I'd end up with plus 24 x to the 4th over 4 factorial. And 4 factorial just happens to be 24. So again, that would cancel with that. We'd end up with plus x to the 4th. So I want you to think about this little box over here to the right. We can put, let's put the nth term, so it'd be plus dot dot dot, easiest nth term of the year, x to the n, right? So do you recognize this function? Do you recognize this pattern? We'll find out later that this series only converges when x is between negative 1 and 1. Like I said, that comes later, but this is still true. Take a minute and think about it. Pause the video, ponder this. This is actually something you have seen, not necessarily in this context, but yeah, this polynomial here is approximately equal to 1 over 1 minus x. But that only works if x is between negative 1 and 1. So pause the video, think about it. When you hit play again, I'll be telling you what it is. So this is actually the geometric series. Geometric series. And with the geometric series, we always have a common ratio. And in this case, the common ratio is x. The common ratio is x. You can see that the first term here is x to the 0, then x to the first, then x squared, so on and so forth. So this is just the geometric series, and essentially what this does is this proves that the sum of the geometric series, as long as we're between negative 1 and 1, is this. If we have enough terms, if we have an infinite number of terms, then the polynomial approximation ends up exactly equaling the function that we had to begin with. Hopefully that's a good thing to think about as we close off this video. And we'll keep practicing this as we move into Power Series, which is section 9.8.